Sir, your microphone is muted.
Oh, sorry about that. Sorry. So let me go back to slide 1. So the 3 types of dienes. So I want to make the announcement. I was unable to load the homework for chapter 16 due to some technical difficulties with Macmillan. So I'm going to look into that today. For any homework due dates, please pay attention to the Achieve website. Also, for you to know the most up to date as far as your grade goes, you need to check Achieve. Sometimes Blackboard will take longer, 24 to 48 hours to transfer your grade. So always go by what Achieve says. So if you read the chapter 16, you'll see that there's 3 types of dienes. You have your accumulated, conjugated, and isolated, and these are going to kind of come out this way. I'm trying to do the best I can with that. So kind of coming out perpendicular. These come out like this. They also go up top like this. And the main difference between the conjugated and the isolated is you have resonance stabilization. Let's just say it takes a proton, you have a positive charge, we can resonance stabilize it right there. We can't do the same thing here, can we? If we put the positive charge here, there's no resonance stabilization here, so no resonance. No resonance stabilization. So this is going to be more stable. So, the 3 types of dienes are your accumulated, conjugated, and isolated. Accumulated pi bonds are perpendicular. The conjugated have a continuous system of overlapping pi orbitals, and that works out really good when we want to have charge stabilization. And then you have your isolated where the pi bonds are separated and there's no conjugation, and we showed an example of that. This chapter focuses on conjugated systems. And you can see that these heteroatoms may be involved in conjugated systems. So sterically hindered base can be used to form dienes by elimination reaction. If there's a proton here, tert butyl, come in here, this would be gone. So that would be an example of a E2 reaction. We also could do it on each side. We form one, and then we're going to form the other one. So we get this right here. So note right here, so single bonds that are part of a conjugated pi system are shorter, 148 picometers versus 153. So that's a difference of 5 picometers. And they say that this is due to the overlap of the sp2 orbitals. Remember, as sp3, there's only a 25% s character. This is about 33%. So the more s you become, the shorter the bond is. And we can remember we have the single bond versus our double bond versus our triple bond. And as we got to the triple bond, it got shorter because our s character got more. So this is, what was it, 50, 33, and then 25%. So as the s character increases, the bond length gets shorter. And that's because with s, an s orbital, if you just think about a true s orbital, it has more overlap than a p orbital. Versus this would be a p orbital overlap right here. So the more s character, the shorter the orbitals and the shorter the sigma bonds. And we discussed that. So heats of hydrogenation show conjugated dienes are more stable. So here is a conjugated diene over here. I'm just going to abbreviate that. And you can see that the stability is 15 kilojoules more stable. Then they say you want to rank these things. Well, this would be the most stable. You can kind of tell if it kind of jumps, it could help each other out. This will be the least, it's isolated. These ones look pretty similar. B and C look pretty similar to each other. Then they talk about this thing in the textbook, cis trans and s trans. If you go back to, I think it's around page 189, I looked this up this morning, you'll see, and I don't know if the hard textbook is the same as the ebook. So if you have the hard textbook, then it's on around page 189 or 190. We talked about cis and trans, where if these are methyl groups here, I just draw CH3, this would be cis. And if this was like this, and these are your methyl groups, this would be trans. So S cis, they say it's cis-like. So it's cis-like. That's what the textbook says. And this is trans-like. So we have an S cis, it's cis-like. So it's, 0 degrees. And then here, this would be 180 degrees. And notice right down here, they're showing you the orbitals. So you could draw in the orbitals like this, and they all overlap. And there's different nodes, then you could draw the orbitals like this, where you have one node, see the one node right there. Then you could draw it with, you know, everything is different. Put it here, here, and here. So we have 3 nodes. You could have one situation with 2 nodes. Here's the one with 2 nodes. Oh, a little better drawing this. So this would be 2 nodes. So they show you the optimal one, which is the most stable. Everything's up, so it's all bonded with each other. All right, so S trans is lower in energy and has less steric hindrance. And they show you cis trans, S cis and S trans. We can see that this is lower in energy. Says the highest energy conformer is not conjugated. So you can see how this is not conjugated. And it's 15 kilojoules less stable. And the non-conjugated one is this one right up here. Oh, maybe where I put this at right here. Says review of molecular orbital theory. 2 atomic orbitals overlap to form 2 molecular orbitals, and you get bonding and you get anti-bonding. So the molecular orbitals extend over the entire molecule. Overlap of the p orbitals in ethylene result in a bonding molecular orbital. So ethylene is this, remember? Oh, there are too many lines. So we have atomic orbitals here. We get molecular orbitals. So you have N AOs equal N MOs. So you see 1, 2, then you got 1, 2. I'll put a star just to indicate the molecular orbitals. Usually only put a star when they're anti-bonding. So these bonding, the orbitals overlap, you can see. With the anti-bonding, they don't overlap. Like I said, you only usually put the asterisk with the anti-bonding. I just did it as a designator for molecular orbitals. And on the next slide, you know, you might want to, this might be the first time you've ever seen this. You know, they're showing butadiene. So what is butadiene? It's this right here. And why don't you go ahead and draw this all out on your own on a piece of paper and draw out all the orbitals. So, you know, you'd have it like one of them be like this, where they're all like this. And then the next easier one is like this. Or they're every other one. So if you draw them out, you're more likely to get it. So I'm going to give everyone a few minutes to go ahead and draw that out. Okay, so you should have all that down now. So let's go on. And they're just showing you the one node versus the no node. So the 4 pi electrons on butadiene will occupy the lowest energy. And let me show you where that's at. So the lowest energy would be here. This molecular orbital theory offers an alternative explanation why the central carbon-carbon single bond is shorter and stronger. That's because you have more overlap. So you have constructive overlap. Here we have one node right here, right? And we're missing that overlap. You know, we have overlap here, we have overlap here, but we're missing it throughout the entire molecule. And then if you know, here they're looking at hexatriene. So kind of the same concepts as butadiene, but now we're looking at 1, 2, 3, 4, 5, 6. Now I'll just draw the first one, you know. So I have 1, 2, 3, 4, 5, 6. And if I'm going to draw the most stable one, I'm going to put it up like this, right? And you can see that one right here. Then the least stable one would be 5 nodes, right? If you have 5 nodes, that means, you know, we have no bonding character whatsoever here. At least with 4 nodes, you know, these middle ones are bonding with each other. These reactions that molecules undergo can often be explained by studying their frontier orbitals. You know, light can be used to excite an electron from the HOMO to the LUMO. So HOMO is the highest occupied molecular orbital. LUMO is the lowest unoccupied molecular orbital. So they're saying that this electron is going from the highest occupied molecular orbital into the, I guess it'd be the new highest occupied molecular orbital when you shoot the electron up, and they're showing that right here. Initially, it's going up here into the LUMO, and that LUMO will now create a new HOMO. So then if this is the HOMO right here, then this has to be the LUMO then right here. It says recall addition of HX to a carbon-carbon double bond, Markovnikov addition, so that bromine go to the more substituted. That's because this cation is more stable right here. So we get 2 products with the conjugated diene. This is called the 1,2 product, and this will be called the 1,4 product, and that's just how it adds, because if you think about this, this would come right here. So it's a 1 addition. Then we have this cation here. Well, that bromine can go in here like this, or it could come in here, right? And then now the positive is over here. So now the bromine comes over here. If it goes over here, we get this product here. If it comes right here, we get this product. All right. So they kind of show you, how I did it. So you can look at, they have a nice drawing out for you. They're saying this is not going to form because this is not resonance stabilized, right? So if it takes it right here, you put the positive here, this is not resonance stabilized. So that's not going to be formed. Let's show you the mechanism right here. So, again, this would be the 1,2 adduct, and this is your 1. That's how you get the 1,4 adduct. So that's how you get your naming right there. So the addition of a bromine to a conjugated diene also results in 2 products. Both the 1,2 and the 1,4 addition occur, and we see that right here. Oh. So the ratio of 1,2 versus 1,4 addition is highly dependent on the temperature. So at 0 degrees, we're going to see the 1,2 addict. At 40 degrees, we'll see the 1,4 addict. And then on the next slide, they show you an energy diagram showing you why this is. So the 1,2 addict occurs faster, kinetically favored. So that's kinetically favored because it's a faster one, but the 1,4 is more stable, it's thermodynamically favored. So if there's a higher temperature, it'll be more likely to go through some thermodynamic transitions to get the 1,4 addict. The 1,4 addict is more stable. It is the more substitute alkene. See, and what do they mean by more substitute? Okay, you have 1, 2, 3, 4. So here's your 1,4 addict. And then you have, one method. Well, I guess you have one group coming off here and one group coming off here. But here you only have 2 hydrogens, right? You have 3 hydrogens total. Here you only have 2 hydrogens total. You have 2 hydrogens versus 3, so this is a more substituted. So at higher temperatures, the formation of the product is equilibrating. The reaction is under thermodynamic control. The product that is more stable will be the major product. And this is the major product then. All right. This is the 1,2 addict forms faster, presumably due to a proximity effect, which is closer. Well, if you get a little more thermodynamics, you can move that bond, push this over, and you can see how the bromine will go in. So many polymerization reactions are a special case of the 1,4 addition. And we see natural rubber and synthetic rubber. They're both formed with the 1,4 addition. I'd like to talk about this introduction to pericyclic reactions. So pericyclic reactions occur without ionic or free radical intermediates. There are three types of main pericyclic reactions. So here we're forming this, we have a diene, we have a dienophile, and we're forming this cycle addition reaction, and we get a six-membered ring. So here we have electrocyclic reaction right here. Note that this was a little different than this right here. We got that from this. So this is different. And we can also have a rearrangement. It's called a sigmatropic rearrangement, and this is their rearrangement. And those are your three main types of pericyclic reactions. So you have your sigmatropic rearrangement, you have your electrocyclic reaction, and your cycle addition reaction. So pericyclic reactions have four characteristics. The reaction mechanism is concerted. It proceeds without any intermediates. The mechanism involves a ring of electrons moving around a closed loop. The transition state is cyclic, and the polarity of the solvent generally has no effect on the reaction rate. So I'll give you some time to copy that down. All right. So changes in the number of pi and sigma bonds distinguish the pericyclic reactions. So here are your three different ones, and they give you a table for the change in the number of sigma bonds and the change in the number of pi bonds. Again, I'll just give you an example here. So with this one, you know, if you have this, if this is coming here like this, you know, how many sigma bonds did we add? Well, we added a sigma bond here and we added a sigma bond here, right? And we added one pi bond here. Well, how many pi bonds did we lose? Well, we lost this pi bond here. I should draw it with a Z. I'll draw it with a, I don't know. We lost a pi bond here and we lost a pi bond here. Well, this is, draw it this way. It's easier. That way you can keep track of it. Oh. Like this. So you can see over in this case, you know, we had 3 pi bonds. Well, now we lost 2 pi bonds, right? But we gained 2 sigma bonds. One type of cycle addition that's very common is called the Diels-Alder reaction right here. It's like all pericyclic reactions, the mechanism is concerted. The curved arrows can be drawn clockwise or counterclockwise, it doesn't matter. But we gain 2 sigma bonds and we lose 2 pi bonds, don't we? So we can see our starting materials. Here's our ending materials. We can see that the ending materials are more stable, so therefore this reaction should proceed with a little bit of energy. But if we get it too hot, we're going to go back. Then we'll have bond breaking. So here we form. So delta G equals delta H minus T delta S. And the pi and sigma conversion provides the minus delta H. So delta S should be 2 molecules combined to form a single product. And you can see that right here. For Diels-Alder reaction, the enthalpy term must be larger than the entropy term for the reaction to be favored. It says at very high temperatures, entropy term opposes. So that's why, when we increase the temperature, here we just have one structure. Here we'd have two different structures, right? So at higher temperatures, it'd rather be in two different structures versus just one. So the reactants are the diene. So here's your diene, and here's your dienophile. So the dienophile needs to possess an electron withdrawing group, or the reaction will require high temperature, which does not favor product formation. Says when an electron withdrawing group is attached to the dienophile. So okay, we have this. Here's our diene. Here's our dienophile. Reaction is generally spontaneous. It says the groups highlighted in red are electron withdrawing. So that means, remember the table electronegativity. We go in, so it's going to pull more electron density away. So Diels-Alder's reactions are stereospecific depending on whether an E or Z dienophile is used. It'd be the Z. It'd be the E. It says an alkyne can also function as a dienophile. And we're going to get this over here. We have some pretty good electron withdrawing groups on this, don't we? All right. So recall that many dienes can exist in a cis-like state or a trans-like state. So that's where you get this S-cis and S-trans. Diels-Alder reaction can only occur when the diene is in the S-cis conformation. So that means, we're not gonna, so we can do it if it's like this, but if it's gonna be like this, we're not gonna be able to push these electrons how we want to. So this is not gonna happen. And we'll do one more slide, then we're going to take our break. So diene's trapped in an S-trans conformation. So we have the S-trans right here. Cannot undergo Diels-Alder reaction. So we're not going to do that. Here, this is in the S-cis. You can easily see it right here. What's going to happen is this is going to come up like this. And when that comes up, this point's going to push up. And you can see that point pushing up right here. So I'd like to take our break right now. We'll come back at we'll take a 10 to 15 minute break. So we'll come back at 11:10 and we'll continue on. All right, everyone, I hope you all enjoyed your break. We're going to continue on. I don't see any questions in the chat box, so must be going pretty good. So we last left off where we said, here is a, if we just go back to our little definition, the S-trans is trans-like and S-cis is cis-like, and here we have the S-trans. You can see that right here. We have the S-cis, and we're going to get a reaction here, but we're not going to get any reaction with this one. It says cyclopentadiene is so reactive towards Diels-Alder reactions that it reacts with itself at room temperature. So that means, okay, here's one, and all they did was turn this. They just rotated it. Let me see something. I guess it rotated 72 degrees. Anyways, here's what the reaction is going to take place right here. We have dicyclopentadiene. This is going to come up, and you see this point coming up right here. We still have this 5-membered ring right here, don't we? And here you should see it. 1, 2, 3, 4, 5. We still have that 5-membered ring. So when biocyclic systems form, the terms endo and exo are used to describe the functional group positioning. So there's two bridges here they're saying. So here's your first bridge. They call this the longer bridge. See, this bridge has 2 carbon atoms. It's the larger bridge. Here's your shorter bridge right here. It only has 1 carbon atom. So it says exo is anti to the larger bridge. So here we have exo. Here's the larger bridge right here. So it is exo. Endo is syn to the larger bridge. So this would be the endo product right here, if we compare it to the larger bridge. So the electron withdrawing group. So here we have some electron withdrawing groups. You know, they should have just drew it like this for you to see it better. And the endo product is the major product, and the minor product, or the exo product, is the minor product, and it's in relationship to the bridge, to the larger bridge. So here we have the 2 carbon bridge. You know, here you just have a 1 carbon bridge. I'll just put a circle around it. So the relationship is to the larger bridge, and so we do get mostly the endo product. So the endo transition state benefits from favorable interaction between the withdrawing groups and the developing pi bond. And they're kind of showing you why the endo product is more stable. So there's a favorable interaction between the developing pi bond and electron withdrawing groups. Here at the exo position, it's just they're too far apart, you know, so there's really no interaction. The endo transition state is lower in energy, and so the endo product forms faster. So here we have the endo versus the exo. And that's, so even though the exo product, the potential energy is lower, you can see if we just look at from this point right here, if I make this our baseline, this transition state right here, we'll call it TS. Or, you know, activation energy. This energy difference right here is a lot less. It looks even in this to be even more than half, Therefore, we're going to form the endo, more likely to form the endo state than the exo state, even though the exo state in the end is more stable. So if you had a bunch of energy you could throw at it, you could probably get to the exo state, but if you don't have the energy that you're throwing at it, then you're going to be more likely to end up in the endo state. And the only way to really know that is to experimentally determine this. So only one regiochemical outcome if the diene or dienophile is symmetrical. So here we have a symmetrical diene. There's only one possible outcome where we put this, the aldehyde right here in this position. Here we have a symmetrical dienophile. So that's if the diene or dienophile is symmetrical. So this is not symmetrical right here, right? This is not symmetrical. But since this one is symmetrical, we only have one regiochemical outcome. If the diene and dienophile are both unsymmetrical, so now here they're both unsymmetrical, then we have two regioisomeric products are possible. It says one of the regioisomers is formed as a major product. The reaction is regioselective. And that has to do with the charge distribution. So if you can just imagine, if you just kind of flip this the other way, it would be the other possible outcome right here. And this is going to be your major product. Any questions so far? So just saying, consider the location of the partial charges. The alignment. It says consider that. So here we're going back to the molecular orbitals where we have the more stable. You have no nodes here. It's all bonded. Here we have, and this is talking about butadiene. And this is your 1. See how you get 1,3 butadiene. says for the Diels-Alder, the HOMO of one compound must interact with the LUMO of the other. So that's where they're saying the HOMO must react with the LUMO of the other. And they show an example of that on this slide right here, where the HOMO is interacting with the LUMO. So with an electron withdrawing group, remember if you have some type of oxygen, chlorine, some type of electron withdrawing group, the dienophile's LUMO will accept electrons from the diene's HOMO. That's what they're showing right here. This is going to accept those electrons. And here's ethylene right here. So with an electron withdrawing group, the dienophile's LUMO. So here's your dienophile. Sorry about that. This is the diene. And here's your dienophile. So dienophile's LUMO, okay, our LUMO, our lowest unoccupied molecular orbital, will accept electrons from the diene's HOMO. And this is shown right here. So they're just trying to show you using molecular orbital theory, how and why this happens. Any questions on that? All right. So the phases of the reacting molecular orbitals must be symmetrical. In other words, if there's a conservation of orbital symmetry, then the reaction is symmetry allowed. You can see we have, and they color code the phases for you so you can see these phases are alike and these phases are alike. So we're going to have this reaction proceed. To note the carbons that change their hybridization from sp2 to sp3. So they become more P-like. This is similar to a Diels-Alder 4+2 cycle addition. The reaction below is a 2+2. We have ethylene plus ethylene. You can just kind of imagine how this is going to take place. So the reacting molecular orbitals, the HOMO and LUMO, can be analyzed to determine if the reaction is symmetry allowed. So now we'll see if it's symmetry allowed. So LUMO of one reactant must have the same symmetry as the HOMO of the other reactant for the reaction to occur. And right here, this is so these phases do not line up, right? This red one and the blue one, they're not the same phase. So the reaction is symmetry forbidden. So we're not going to have this reaction right here. I should do this, and then I should put a big X over it. It says cycloadditions are only possible when light is used to excite an electron. So you have to excite this electron here first. And then now once you excite that electron there, now you can have the phases line up with each other because we're in a different, the HOMO has changed. See, before, just look at the colors right here. You have red and blue, and here you have blue and blue, right? I'm just going to call it B and B, and this one is R and B. And these two phases now line up, so this reaction now can proceed, but it had to take a little bit of energy for it to happen. So electrocyclic reactions, a pericyclic process where a conjugated polyene undergoes cyclization. As overall a pi bond is converted to a sigma bond. And there's less strain when you have 6. This is a 6-membered ring, right? And here's a 4-membered ring. This had more strain to it. So when substituents are present on the terminal carbon, stereoisomers are possible. So we have some substituents, right? And we can get, with these interactions with light or heat, we can get, these stereoisomers. So if you're going to have the one up and one down plus the enantiomer, they don't show it, but we'll draw it. You're going to have the other one, right? It says, note that the use of light versus heat yields different stereoisomers. And they explain this by the conservation of orbital symmetry explains this observation. So depending on the direction you're going in, light or heat will have an impact on which, product that you form. And we'll end it right here. So it says, consider the stereochemical outcome resulting from the thermocyclization of a pi system with 3 conjugated pi bonds. You can see we get, in one situation, we have the substituents both pointing up. In the other situation, we get both enantiomers. So room temperature is often sufficient to facilitate thermocyclization. Like I said, we'll come back to this tomorrow. Hopefully Macmillan has the homework issue solved, so I'll look into that today. So hopefully tomorrow we're able to get on with the homework for chapter 16. If not, we'll go into chapter 17 if Macmillan still has their problems. So that'll kind of depend on Macmillan. So I hope everyone has a great day. I'll see everyone tomorrow. If you have any questions, you can please stay back.